Shall we start it?
Yes, please go ahead.
Okay. Start this. So welcome to our seminar series. So this event is a students organized organized by IEEE Electronics Packaging Society student chapter at University of Waterloo. We also like to give a special thanks to our University of Waterloo at ECE department and Andrew Pinus for the incredible assistance. So our events will be around 45 minutes talk, followed by 10 to 15 minutes of Q&A. If you, throughout the presentation, if you have questions for the speaker, please use the Q&A function. They will be presented to the speaker during the Q&A section. Alternatively, if you would like to pose your question to the speaker live, simply use the raised hand function and we can unmute you. Just a friend reminder that this seminar is recorded. So let me give a brief introduction to the speaker. Dr. Yating Wan is an assistant professor at King Abdullah University of Science and Technology. Previously, she works in Professor John Bauer's group at UCSB from 2017 to 2022 as a postdoctoral research associate. Her research interests are in silicon photonics with special emphasis on integration of on-chip light sources for data communications, biosensor, bioimaging, energy harvest, machine vision, and quantum information processing. She received the 2016 to 17 School of Engineering PhD Research Excellence Award from Hong Kong University of Science and Technology. 2021 Cleo Tin-Ye Lee Innovation Prize. 2018 Pierce Young Scientist Award. 2021 OGC Best Young Scientist Award, and was selected as the finalist of 2022 Rising Stars of Light. She has published more than 60 peer-reviewed research papers, including 36 first author journals and conference papers, and 8 journal covers. So today it's our honor to invite Dr. Yating Wan to give us a talk on the advance in quantum dot lasers and integration with silicon photonics integrated circuits. Welcome, Dr. Wan.
Thanks, Ci. Shall I share the screen?
Yes, let me stop sharing. Okay. Yeah, go ahead.
I still cannot share the screen.
Oh. Let me share. Where's the stop sharing? Sorry. Okay, go ahead.
All right, thank you. So can everyone see my slides now?
Yes, we can.
All right. Hi, everyone. I'm Yating. It's very nice to meet everyone virtually. And great thanks to for the introduction from Ci and for the opportunity to present my work here in this great forum. So in this talk, I will talk about integration of on-chip light sources in silicon photonics. Most of the work I present today was done during my postdoc research in Professor John Bauer's group in UC Santa Barbara and a collaboration with Intel, and it's now continued in-house. Probably some introduction of myself. So I received my bachelor degree at General University and PhD degree at Hong Kong UST. I graduated with PhD Research Excellence Award and then joined Professor John Bauer's group at UC Santa Barbara as a postdoc for the next 6 years. In 2021, I received the Cleo Tin-Ye Lee Innovation Prize and then joined KAUST as an assistant professor. So during the past 10 years of work in silicon photonics, I focused on the integration of on-chip light sources to accelerate optical I/O innovation in performance scaling and integration, and boost its application in data communications, machine vision, and quantum information processing, etc. So main achievements in my work includes a variety of high-performance active devices integrated on silicon. So this kind of dense device integration with on-chip lasers will be critical for a number of envisioned future applications, and has produced this following pioneering results and this more than 60 research journals, including 36 first author papers and 9 prestigious journal covers. And I was awarded with this kind of awards. So in this seminar, I'll first give you an overview of silicon integrated photonics, and then discuss my latest research achievements in high-performance quantum dot devices, lasers integrated on industry standard silicon substrate. So various types of lasers have been demonstrated with over 10 world record performance matrix, and two different integration schemes has been explored here, the monolith integration approach and heterogeneous integration approach, to integrate these quantum dot devices on silicon platform with the aim of process simplicity and high device performance and commercial viability. And then finally, I'll end with a conclusion and a future perspective in exploring photonic integrated circuits with on-chip lasers for different applications. So first, what is integrated photonics? Integrated photonics is an emergent branch of photonics in which waveguides and devices are fabricated as an integrated structure onto the surface of a flat substrate. So this requires continual improvement in volume and functionality and a reduction in cost and power consumption. So silicon-based integrated photonics could address these requirements, as it relies on the well-established microcavity fabrication, so that it's possible to fabricate very complex photonic circuits that process and transmit light in similar ways to how electronic integrated circuits process and transmit electric signals. So today, Facebook, Amazon, and Google alone run massive cloud computing data centers. The data center traffic is projected to grow at 25% compound annual growth rate for the next 4 years. And COVID-19 is accelerating the transition to a digital economy, and online schools and virtual conferences, for example, this seminar, are all driving this photonic revolution. So fiber optics has already replaced copper interconnects in long haul and metro communication links, and now a similar trend you see in data interconnect links is happening at increasingly short length scales down to 1 meter. So with this kind of strong driving force, silicon photonics is making a real impact and is believed to be probably the best platform and to make this transition, and it has a very large big impact in both industry and academia. So you see from the market, the silicon photonics market is projected to grow from $1 billion in 2020 to $3 billion by 2025, with a very good high compound annual growth rate as high as 23%. And you see, so, and also starting from this pioneering work from Sarib and Bennett, and with the milestones many achieved in UC Santa Barbara, Intel, IMAC, and Ghent University. So this is the silicon photonics article published per year as a function of the year, and you see that is exponential growth in the number of articles published per year. So so the impact of silicon photonics in academia is also growing rapidly. And nowadays, a variety of photonic devices can now be put on silicon, includes low-loss waveguides, modulators, switches, detectors, MEMS, and nonlinear materials. So the foundry efforts across the entire world, especially in the North America, Europe, and Asia, are quickly pushing this commercialization and wide deployment of silicon photonics, with the many promised advantages like good thermal and mechanical properties, extremely low loss waveguides. We're talking about as low as 0.03 dB per centimeter, and excellent optical confinement, and the 300 millimeter wafer scale, high throughput processing, and high volumes and a low cost. So increasing number of players you see in the race of silicon photonics. For instance, Intel's 100 G transceivers based on silicon photonics are now in volume production. Cisco is currently simplifying the 100 G pluggable optics and beyond. Acacia engages for coherent silicon photonics. AIM could provide a wafer scale test, assembly, and packaging for silicon photonics chips manufactured in the 60 nanometer node, and global foundries are working on 300 millimeter wafers. So a lot of things going on in its foundries. However, in some aspect, silicon is kind of a bad material for photonics. So you see silicon is indirect bandgap material, so it's not a good light emitter. So actually you see the best over the past 20 years, the best group 4 material has made the laser has special current as high as 300 kiloamp per centimeter square, and actually which is like more than an order of magnitude than what can be achieved in the direct bandgap SOFR material. And also the device made from silicon and germanium can only cover modulation and detection for wavelengths around the near infrared, but are not suitable outside that range. Silicon is reciprocal, so isolator and circulators are not possible. So all those things like make silicon germanium unsuitable for high performance lasers or amplifiers. And as a result, so overcome inherent limitations of group 4 materials for gain, efficient modulation, and detection and wavelengths outside near infrared requires we integrate the 3-5 materials together with the silicon photonics platform. So given that lasers were the primary missing component in the silicon photonics platform, the 3-5 and silicon integration research has been focused on generating efficient lasers. So to integrate 3-5 lasers onto the silicon substrate, this is the first generation, which is a hybrid integration. So basically, people fabricate the 3-5 device and the silicon device separately, and then mount the 3-5 dies on top of the silicon photonics dies using externally coupling. So one obvious advantage of hybrid integration is that it has a capability to optimize the active and passive separately without sacrificing for process compatibility. However, this kind of optical packaging with optical alignment often occupies over 90% of the total cost. Efficient optical coupling of the 3-5 to the silicon photonics waveguides usually relies on alignment with precision in the lower micrometer or even sub-micron range. So this often requires slow and expensive active alignment techniques, where the coupling efficiency is pretty low. And moreover, like additional devices such as a microlens, prisms, or micromechanical carriers are needed to adapt the mode, field size, and the emission direction of the 3-5 light source to that of silicon photonics circuit, and that lead to large footprint and a limited scalability. So heterogeneous integration, on the other hand, is another technique that actually bonds the unpatterned 3-5 thin films to the silicon wafers at the early to middle stage with a coarse alignment, and then we can define the device by lithography on a full wafer scale. So the overall efficiency is very high, reaching coupling loss lower than 0.5 dB per interface. And with the chip maker Intel, this device became the first laser on silicon used in mass-produced products, transceivers, that begin shipping by the millions in just the last few years and is generating over 1 billion of revenue nowadays. In addition, this technique not only offers elegant paths for the inclusion of a laser source on a silicon photonics platform, but also make it possible to flexibly add different functionalities, different materials onto the same chip, despite the material incompatibility. For example, the indium phosphide materials for telecom communication, the gallium arsenide-based material for 850 nanometer VCSEL, lithium niobate for modulators, InGaAs for photodetectors, silicon nitride, silicon oxide nitride for ultra low loss waveguides, and the YG thin film for isolators. However, the associated technical complexity is still considerable, particularly with respect to the stringent requirement of the ultra clean and extremely smooth surface before the bonding. Moreover, you have to use a 3-5 substrate that is costly and impose a limit on the maximum bonding size set by the largest available 3-5 substrate, which is typically no larger than 200 millimeter for GaN oxide and 100 millimeter for indium phosphide. This is much smaller and more expensive than a silicon counterpart. So considering that the 3-5 substrate cost, the monolithic integration through direct epitaxial growth is a more economically favorable option, and also it can provide the best natural heat sinking for laser operation. However, the fundamental material difference between the 3-5 and silicon during the epitaxial growth can generate a high density of crystalline defects, including primarily the threading dislocations, stacking force, and antiphase domains. So this kind of dislocations have associated with trap states that act as non-radiated recombination centers that tend to gather an atmosphere of point defects that promote further growth of dislocation networks, and finally, this large network of dark line defects that severely degrade the device performance and shorten the lifetime. So actually, research has been conducted since the 1980s to grow these quantum well-based lasers directly on silicon. Well, they have got quite a promising improvement in terms of like special current density and light output power and external quantum efficiency up to 87%, quite promising. However, the aging test show the maximum device lifetime is only 200 hours. And this was even obtained with an ultra-low spreading dislocation density of just 2v6. And that is obtained in a time Q-mean growth of 10 micron SiC germanium silicon, and silicon buffer, and off-class silicon substrate that is not CMOS compatible. So in addition, if you want to further lower the spreading dislocation density below this value, this is very difficult. And since the interactions between the dislocations is the only mechanism to filter out the dislocation in both films, with such low spreading dislocation density, the possibility of two dislocations meeting each other to annihilate is extremely low. So defect-free 3-5 on silicon, or even defect levels comparable to that of the state-of-the-art 3-5 wafers, is theoretically never be available. So in this scenario, how can we improve 3-5 lasers on silicon by orders of magnitude? Well, the first strategy is still try to reduce the defects in the semiconductor material itself, in addition to spreading dislocation, but also antiphase domains and misfit dislocations. So to deal with antiphase domains, people finally find that a thin layer of gallium phosphide buffer can efficiently suppress its effects. And nowadays, this 12-inch gallium phosphide silicon wafer are commercially available with no antiphase domains. And to deal with the spreading dislocation density, people can still make it even smaller. So this is the most advanced asymmetric step graded filter. With this kind of filter structure, a surface spreading dislocation density as low as 1e6 can be achieved within just 2.5 micrometer of 3-5 layers. This is quite close to the theoretical limit, and it is quite trustable as it's verified by both the electron channel contrast imaging and the plane view transmission electrical microscopy. And finally, to combat with the misfit dislocations, so here a thin string quantum wells was inserted as trapping layers above and below the active region, which can efficiently block 90% of the misfit dislocations away from the active region, and is experimentally confirmed through the cell measurement. Through this great innovations in the growth to combat the antiphase domains, the spreading dislocations, misfit dislocations, we can got pretty high quality 3-5 buffer on CMOS compatible 001 silicon substrate. And in addition to the reduce the defects in semiconductor material itself, so a more important strategy here we are using is to change the active region from the quantum wells to quantum dots. So currently, the most dominant active region is still quantum wells, either for the heterogeneous or the hybrid integration or the monolithic integration. We are talking about in the third method. So there is definitely a transition from the quantum well to quantum dot region. So that why, due to the three-dimensional confinement of carriers, so quantum dots can promise a lot of performance advantages over its quantum well counterparts, including high temperature tolerance that allows for robust cSWaP operation up to 220 degrees C, the low threshold currents that is capable to support low energy consumption, the reduced lateral diffusion that can reduce the sensitivity to defects and also sidewalls. So the former can enable scaling of laser cavities to smaller devices for high density integration, and the latter can enable growth on 300 millimeter silicon wafers with very high reliability. And finally, this ultra low line with enhancement factor, or we call alpha factor. So this can reduce the sensitivity to reflections. So people don't need isolators that are bulky and expensive. So these last 2 points are very important, and I'd like to especially emphasize. So for the first, the ultra small line with enhancement factor. So this value for quantum well typically is 3 to 5, but quantum dot is 15 times smaller. So from this scaling factor, the critical optical feedback level for coherence collapse is closely related to this alpha factor. And a quantum dot exhibit over 50 dB increase in this value compared to quantum wells. So that when 90% of light reflected back to the laser, the quantum dot doesn't have any coherence collapse, as evident from this as evident from this optical and optic spectrum. But on the other hand, for a commercial quantum well device, even at a very low feedback level of minus 25 dB, you can see this coherent, complete coherence collapse. So this is very important to data communication systems, because with this reflection tolerant quantum dot active region, we don't have to incorporate external Faraday rotation-based optical isolators into the system to block the undesired reflections, which is bulky, expensive, and greatly complicates the packaging and can add additional insertion loss. And the second part we are talking about is the carrier diffusion length. So the typical value for quantum well of this carrier diffusion length is around 10 micron, but quantum dot is 10 times smaller. So in the case of a relatively high spreading dislocation density, so we highlight as this red lines. So carriers in the quantum wells are free to move around in the plane of the well, and they can encounter a defect before we combine radiatively. In a quantum dot, however, due to the reduced carrier diffusion length and the reduced carrier mitigation to dislocations, the chance to be trapped by the dislocation trap state was greatly reduced. So, for example, in this TEM image, the red points refer to the defects, and the yellow dot refers to the quantum dots. And you can see that even with a very high spreading dislocation density, we are talking about 3A something. But because the dot density is still more than 2 orders of magnitude larger than the dislocation density, and because each dot is independent, one spreading dislocation line in active region can only kill one or a few dots, and the majority of the dots are not affected. So device can still work efficiently. So this much improved defect tolerance gives rise to record device lifetime on silicon. So while remember the maximal lifetime of quantum well lasers grown on silicon as only 200 hours after several decades of research development, our generation 1 quantum dot device already show lifetime of 800 hours at 30 degrees C, and later 100 years of lifetime at 35 degrees C. And our most recent results show a remarkable improvement of 1 million-hour extrapolar lifetime at 80 degrees C. So this is much better than our first generation of device, and also orders of magnitude better than any kind of quantum well lasers actually grown on a silicon substrate. So with this material development, there is a lot of recent progress of quantum dot devices grown on silicon, such as this sub-wavelength optically pumped microdisc lasers, the submilliamp special electrically injected micro lasers, this couple cavity tunable lasers, this high-speed DFB lasers, this isolator free system demonstration showing a path towards high volume, low cost transceivers that can be scaled to beyond 1 terabit per second. There's 20 gigahertz molecular lasers with high channel count and excellent IF performance. There's high gain, high saturation optical power, semiconductor optical amplifiers, and this ultra low dark current photodetectors, which is around 5 orders of magnitude lower value than a state-of-the-art germanium photodetectors on silicon. So I will briefly talk about some of the devices. So for the most standard Fabric Pro quantum dot devices on silicon, we have achieved this world record performance of 87% injection efficiency, 175 milliwatt output power, 0.65 milliamp special current, and theta operation up to almost 120 degrees C. So even today, it still represents the best quantum dot laser performance on silicon, and this can sufficiently meet the basic requirements for data applications, where it's desirable for laser to have continuous wave operation up to 80 degrees C with tens of milliamps thresholds and reasonable output power of 1 to 10 milliwatt. And in optical transceivers, the power consumption of the laser can comprise a significant fraction of the total transceiver power budget. And microcavities can perfectly solve this issue, which can confine the light to small volumes with a resonant recirculation, and its advantages to make ultra low threshold and small footprint light sources. However, these quantum well-based microcavities devices normally experience serious sidewall scattering and recombination as the resonance size is reduced to tens of micron. So this can result in faster rollover, increased threshold, and a low operation temperature. And quantum dot, on the other hand, has reduced sensitivity to recombination at device sidewalls and other surface defects. So by combining the Whisper gathering cavity with carrier localization of quantum dots, the optically pumped device can have a size as small as 4 micron in diameter and a threshold as low as 200 milliwatt, and it can be scaled to subwavelength size with cavity size as small as 0.5 micrometer in radius, threshold as low as 35 microwatt, and a spontaneous emission factor as high as 0.3. So compared to optical pumping, electrical injection of micro lasers is more challenging because the electrometallization is limited by the micro-sized cavity. And here we have a special etching recipe and a sizable passivation technique so that we can form this 4 micron tool mesa with a straight etching profile and a smooth sidewall surface. So the electrically injected microring can have a submilliamp threshold and a maximum operation temperature up to 100 degrees C and a characteristic temperature as high as 175 Kelvin. More importantly, so we can take a close look at in this figure, which shows how the special current change with a reduced cavity radius. And we can see that even at the smallest dimension, which is set by the limit of our lithography tools, the special current is still showing monotonic decrease with the radius, which indicate a very low impact of sidewall recombination. So this kind of downscaling capability, these compact geometries, and the low power consumption are very promising for high density and low power photonic integration. In addition to microring lasers, widely tunable laser is also an important branch of lasers that can provide backup transmitter source and components of wavelength routing devices. So traditional tunable lasers use quantum wells as active region and are typically fabricated through rigorous steps on native substrate or integrated on silicon through wafer bonding. So this kind of structures both are require complicated fabrication, relatively large footprint, and also they have this multiple electrodes for wavelength tuning. But here we use a specially designed halfway coupler as a mode selection filter, and we leverage quantum dots produce the surface recombination effects to enable deeply etched process through the active region. And with this simple and integrable device structure, without using any grating lithography or rigorous process, we demonstrate the first tunable single wavelength quantum dot laser, where these two fabric cavities have slightly different lengths to shape the linear spectrum for wavelength tuning. And we got 14 nanometer wavelength spacing with up to 45 dB substitution ratio over 11 milliwatt output power. So in addition to the material quality and individual quantum dot device performance, a lot of efforts are also needed to form this fully integrated photonic integrated circuits. So today, indium phosphide-based monolithic integration and silicon-based heterogeneous integration are the two most important on-chip integration technologies. And quantum dot-based photonic integrated circuits on silicon can thus be built upon what has been achieved through either monolithic or heterogeneous integration. So in the first platform, all the photonic functionalities are performed in the 3-5 materials, and the silicon wafer is only used as a handling substrate. So this approach benefits from the lower substrate cost, the larger wafer size, the lower thermal impedance of silicon, and the well-established wafer scale CMOS fabrication, and it can be achieved by rigorous offset quantum dots, intermixing, etc. And following this direction, we previously demonstrated high-performance regrown DFB laser integrated on silicon substrate. And by realizing the very high quality and rigorous capability in gas-based materials, we can enable the possibility to spatially combine different band gaps into one optical chip. So here's the DFB laser growth structure, and which is completed by two-step MB growth. So the first growth is stopped at this 100 nanometer gas layer on top of the active layer, and then a uniform first order DFB grading was dry etched into the gas layer, and we carefully control the grading quality and the following regrowth surface treatment, so that we can get this very high quality regrowth of the rest part, and then we process into this deeply etched waveguide structure. So the laser can sustain single mode operation in the ground state across a wide current range of 110 milliamp with a maximal sun-MOS ratio of more than 50 dB. And the emission wavelengths can cover 1285 nanometer to 1338 nanometer by laser array on the same chip. And by virtue of the very small alpha factor of quantum dots, we are able to perform the system demonstration without optical isolators. And we got an aggregate transmission capacity of 640 gigabit per second using these 5 channels of the laser array with 64 gig mount PAM4 modulation. So the current wavelength range was still limited not by the quantum dots, but actually by the range of grading periods we currently use. And by using a chirped design in the quantum dot region, the gain bandwidth has already been experimentally broadened to 127 nanometer. So the laser wavelengths can also be extended well beyond the current test range, and a 1 terabit data transmission should be achievable. So for the second direction, to integrate quantum dot-based photonic integrated circuits on silicon, we not only use silicon as a substrate, but instead, we aim to achieve low-loss active-passive coupling of 3-5 with the silicon waveguide. And this is something really we call silicon photonics. In this case, compared to the standard heterogeneous process, it requires change from the indium phosphide-based quantum well epi to gallium arsenide quantum dot epi. And thus, we need different material systems and thus different device design and process optimization. So here is the schematic showing the quantum dot laser integrated on the SOI substrate, which consists of this hybrid 3-5 silicon active region coupled to the passive silicon waveguides by both ends. So the process starts with the passive waveguide process, the subsequent wafer bonding and substrate removal, and then we etch the 3-5 mesa precisely down to the 150 nanometer N-gas contact layer and try to keep the etch uniform across the whole wafer. So a lot of process optimization was devoted to achieve this smooth, straight side walls so that we can get this very nice 3-5 taper to shape the hybrid active mode to couple into the passive silicon waveguide mode on both ends. And after paddling the P mesa, a separated short transition was done patterning to pattern this N-gas contact layer. And then after that, the metal stacks was deposited and the device was passivated and the via was opened for the pro metal deposition. So here the laser shows a special current of 4 milliamp, a signal saturation ratio of 60 dBm, the cSWaP operation of 75 degrees C, and the 3 dB bandwidth of 13 gigahertz, and fundamental line width of 26 kilohertz. So what I want to emphasize is the last 2 points. So for the modulation bandwidth, this has always been recognized as very difficult to attain for quantum dot lasers due to the lower confinement factor, the finite intraband relaxation time, and the gain saturation effect. So to date, even the best reported modulation bandwidth of the O-band quantum dot DFB laser grown on a native substrate is limited to be around 10 gigahertz. But here, we got a record high value of 13 gigahertz with just a polished facets, which means there still remain a lot of room to improve the modulation performance. For example, adding appropriate facet coatings, depositing metals on a thick dielectric for low capacitance, etc. So we can make the real value even far more than 13 gigahertz something. And the second point is the line width. So still remember that we emphasized many times that the one very important aspect of quantum dot laser is that it has a very small alpha factor. And that small alpha factor can contribute to significant reduction in the laser line width. So here, the Lorentz line width was just 26 kilohertz. This is an order of magnitude lower compared to the typical solitary quantum well-hinged laser line width, which is several megahertz. So this table compares the device performance of this work and previously reported work. So what we want to emphasize is that the heterogeneous quantum dot DFB laser with a silicon waveguide can significantly outperform monolithic quantum dot DFB laser without a silicon waveguide in terms of line width, bandwidth, signal spatial ratio, etc., which we are very excited about, as it shows a synergistic relation between the unique capabilities of 3-5 quantum dots and a silicon, allowing for not only a reduced of cost due to the economy of scale, but also much better device performance, exceeding what can be achieved with purely 3-5 quantum dot devices, which means when you put lasers on silicon, you not only get a better substrate, you actually get better lasers. So following this direction, we now cooperate with Intel and is using Intel's 300mm silicon photonics platform to pattern the passive parts to be bound with the quantum dot epi. So the heterogeneous integration has already been very successful in Intel with mass production lines. So here, by just changing out the bonded quantum well epitaxial material for quantum dot on silicon substrates structures, there will be substantial opportunities to build upon what has been achieved through heterogeneous integration to both improve performance and reduce cost. And looking in the future, currently the biggest driver in future developed silicon photonics is still for datacom. But beyond the datacom, the dense device integration with on-chip lasers will be critical for a number of innovation future applications. So for optical phase So for the LiDAR applications, the optical phase array-based LiDAR, so the dense integration, high power will definitely be a big advantage. And for photonic biosensors with this kind of integrated light source, the price will be significantly reduced and the size will be significantly reduced, which is very important for portable devices. For neuromorphic photonics, the current approach of fiber packaging is of course the most straightforward way to get light into the chip. But in the future, especially spiking neural networks, optical laser source will be required so that all optical signals will be confined within an integrated circuit package for efficiency, stability, and scalability. And furthermore, for this quantum things, So silicon photonics already shows promise as a platform for quantum computation, and quantum dots show promise as a source of entangled single photons compatible with the proposed computation schemes. The related research is still in the fundamental stage. But if quantum dots are already being integrated in silicon photonics for classical applications with established process, then it makes sense to grant an extra consideration in designing future quantum computation platforms. So by leveraging the trade features of integrated silicon photonics and advanced Intel PDK and process, on-chip lasers will revolutionize these applications for substantial performance gains, green solutions, and mass production. So to conclude, we have achieved a lot of progress in the last 6 years in on-chip lasers with silicon photonics. So laser integration for silicon photonics is definitely the key to advanced photon integrated circuits and the solution that can best leverage economic scale of silicon while maintaining the highest yield will win. We look forward to transform this technology to something that can really influence the industry. And finally, and most importantly, I'd like to thank my supervisor, Professor John Bowers, and the UCSB group. And also, I'd like to thank my collaborators in Intel, in HKUST, in Harvard, in HP, in Quintessence, in Cardiff University, in Sandia National Lab, in IQE, in Zhejiang University, in CUHK, in National Central University, in Shanghai Tech, for contributing so much to this work. And for the second part, I'd also like to use this opportunity to put some small advertisement. So PhD student fellowship positions are now available in my group for 2023 admissions. Successful applicants will be offered full-time scholarship, which is worth approximately $75,000 a year, including the top-notch housing, stipend, health insurance, and airfare. Also, the KAUST Global Fellowship Program is also open to applications for postdoc. So a maximum 10 global fellowships will be awarded and each year. So this program provides a 3-year fixed-term contract and an annual stipend of $75,000 with additional benefits including medical insurance, relocation allowance, schooling and accommodation, and access to the state-of-the-art research facilities for semiconductor research. So our core lab provides facilities for semiconductor material growth, device nanofabrication, and characterization. So these facilities are supported and maintained by excellent and very experienced scientists and technicians to make full use. Yeah, let me see. This is our nanofabrication core lab. It consists of world-class lab space, including 2,000 square meters of clean room facilities, a microfluids lab, and a thin film deposition lab, including metrology, bonding, etching, deposition, thermal processing, lithography, and mask making. We can fabricate and characterize a variety of structures and devices at the nano and micro scale for many applications such as laser diodes, biosensors, solar cells, supercapacitors, transistors, flexible electronics, and others. There are many new equipments that are not shown in this video. For example, the newest maskless aligner from Hindenburg that will be installed this year, which is able to expose a 100mm wafer in about 30 minutes and achieve minimal feature size around 0.5 micrometer. With overlay accuracy better than 200 nanometer. And the newest Oxford SB etcher, the 100 Cobra, will also be installed around the same time, which is very good for etching in phosphide, gallium arsenide, and gallium nitride-based materials, in addition to atomic layer etching process. And this is our imaging characterization core lab. It has a broad array of capabilities in imaging, structure, and and spectroscopy characterization include electron microscopy, nuclear magnetic resonance spectroscopy, physical characterization, optical microscopy, micro-PL, and surface science. So actually for TM alone, we have 6 very advanced tools. This is very rare in any universities across the world. Okay, so something more about the campus. So KAUST actually ranks #1 in the world for citations for faculty in the QS World University rankings, and top 20 in the world of fastest rising universities for high quality research output. You can see in its videos that KAUST is a very beautiful place with Brazil just steps away. We provide work, play, life environment with state-of-the-art fitness and facilities and ample recreational amenities. So, for example, an infinite pool with its magnificent view overlooking the sea, a 9-hole par 36 golf course, full range of a scuba diving course from open water all the way up to a dive master, numerous fine dining and casual fare restaurants, private charter boat cruises, snorkeling and diving trips, and traditional fishing trips, etc. So there is a wide range of activities and opportunities to keep fit, active, and entertained so that you can work hard and play hard. And also KAUST is quite international. It attracts students, postdocs, and scientists and faculties from all around the world in 104 nationalities. Actually, KAUST ranks first in the percentage of international students and first in the percentage of international faculties. So you will enjoy the diverse and international university community of faculty, students, staff, and the cross-disciplinary organization between academic divisions and research centers. And KAUST students are quite successful. 65% are employed in many top industries, and the remaining 23% are in academia in great institutions. And actually, before you make this big decision, we also offers short period intensive camps and schools during the specific seasons to try to have students to develop their practical and creative skills and introduce them to research projects in various science and technology. So we have this microtronics winter camp, and it's now open for application. So it's scheduled in January to February and focus on integrated circuits, 3D printing, and self-assembly. And later, we will also have this photonics summer camp in July that exposes participating students to the frontiers of photonics research, including energy harvesting, biophotonics, semiconductor lasers, and photonic communication. And we also have this visiting student research program that provides a longer training time from 3 to 6 months, so you can know more about the campus and whether you really like the research or not. And so if you're interested in joining our group, please send your CV, your research plan, and your transcripts to my email. I also welcome undergrads to participate in research projects and gain experience. So expect the student to be very self-motivated, have creative ideas, and willing to tackle important problems. I'd be happy to check through emails or video conference before your application. Again, you are most welcome to know more about our lab and the applications through our website here. So thank you very much for attention. I'm happy to take questions now.
Yes, thank you so much for Dr. Wan's very excellent talk. So if you have questions, you can raise your hand and we can unmute you, or you can leave a question in the Q&A box. Yeah. Maybe I ask first question for Dr. Wan. We see that for the quantum dots laser, the line width enhancement factor is much lower than quantum well lasers. For the quantum dots laser is 0.5. So what's the narrowest bandwidth for the quantum dots lasers?
What is a line width, right?
Yeah.
Okay, yeah. So alpha factor is related to two things. The first is the feedback, right? So it can increase the tolerance to feedback. The second thing is, so narrow line width enhancement definitely to relate to narrow line width. So it can contribute to reduction of the line width. But actually, we can hardly see what is the theoretical limit. So for example, if we just fabricate a pure DFB laser, so we don't have any external strategies to further lower the line width. The smallest one we get is 26 kilohertz. But if you can like couple the laser to some external cavities, like some double rings, some high Q cavities, these external cavities can further lower the line width, probably to much lower value than what these external cavities can bring the quantum well lasers. So remember, the external cavities can lower the quantum well lasers to like sub-hertz. So you can imagine what these external cavities can lower the quantum dot lasers. Okay. So line width is related to two things. The first is like the alpha factor, which is something internal, but at the same time is related to some external cavities. Yes. Mm-hmm.
Okay. Yeah, thank you. Any questions?
We do have a question from the audience from William Wong.
Yeah.
William, please go ahead.
Okay, thank you. Okay, yeah, now I'm unmuted. Thank you for the talk. I really enjoyed the work that you presented. I have a quick question on the heterogeneous integration. First, the question is, how well can you bond the two wafers together in terms of, the opto-electronics and the, I guess it was the SOI wafer that you had in the diagram, in terms of, the alignment and the, I guess the electrical contact. And my second question is, how can you have you considered extending this technique to putting 3.5s onto other platforms, and other platforms meaning like non-silicon types of platforms, maybe like flexible substrates or something that has other functions that are beyond, say, silicon or CMOS.
Thank you for your question. That's very good questions. So for your first question, so the beauty of heterogeneous integration is that you don't worry about alignment. So because the alignment was performed, because you only need to bound this area to cover this area of devices, and the alignment was done during the following lithography. Because here we just bound some unpatterned thin films. So the 3.5 thin films was unpatterned. After this was bonded on the SOI substrate, and then we do lithography. So the alignment accuracy was controlled by the subsequent lithography, not by the bonding. So this is totally different from the hybrid integration. So for hybrid integration, you have to your alignment is very important. So you have to align the laser to the silicon waveguide, right? But here we don't have to worry about it. You just bound roughly like to cover this area, and the accuracy, the alignment accuracy was controlled by the subsequent lithography. So it depending on how advanced your lithography tool is, you can get the kind of accuracy in this alignment. And for your second question, yes, definitely. So the heterogeneous integration, so by one hand, you can bound by different materials to SOI substrate, for example, gallium arsenide, 3.5, like lithium niobate, Valg things. And also you can also bound you can also bound this SRI to different substrate. For example, SOI here, and also silicon carbide is also a very interesting substrate because of thermal, right? And also probably some 2D materials. These are all possible. So that's the beauty of the heterogeneous integration. It's very flexible. It can accommodate different materials despite of their different material qualities.
Okay, thank you. I have a follow-up question on what you just said. How critical are the thermal properties of the I guess the receiving wafer that you bond to? Are you actively considering using that bonded wafer as a way of driving or taking away some of the heat that's generated from the 3.5 materials or the 3.5 devices? And if you are, how is that helping in terms of the actual performance of the devices?
Oh, that's also very brilliant question. You are not a student, right? You really know this field. So actually, thermal is a big problem because so for SOI substrate, because there is a 1 micron oxide. So this is very bad for thermal. It's very bad for thermal dissipation. So so what we do is that we actually act at a thermal shunt so that we can conduct the heat from a laser directly to the silicon substrate. So this is some strategy to overcome the heat problems, but we definitely need more optimization. And also the second part is for the thermal management. So normally as the bonding temperature is not a problem. The bonding temperature is only 300 degrees C. So if you put pattern the silicon waveguides, put some modulators at detectors already on the silicon SOI wafers, and then bond and then do the post process, the thermal budget should be fine because the bonding temperature is not. We are not talking about like 500, 600 regrowth temperature. We're talking about just a 300 degrees C temperature. So it should be fine. I'm not sure if I answered your questions.
Yeah. No, I was relating to the operation of the device. Like, have you ever calculated or simulated the temperature difference that you can heat sink the laser compared to, say, having it operate without it bonded or integrated with another substrate?
So this I think this needs more comprehensive. I don't have a clear answer for now. We definitely need more comprehensive analysis.
Right. Okay. Thank you very much.
Thanks for your question.
Okay, so next, Eric Liu have a question. Can we unmute it?
Yeah, thank you. Very nice presentation. And I have a quick question. You compare the quantum wire and the quantum dots for the lifetime. Quantum wire is less than 200 hours, and the quantum dot is much more. The lifetime much better. So that's one experiment. Another experiment about maybe page 17 about coherent collapse. You mentioned the quantum dot is much better than quantum wire. Could you please explain what's the reason? Yeah.
Oh, so this reason, so you see the quantum dot has this 3-dimensional confinement so that it has delta density of states. So this kind of things, so this is like related to the density state so that it can has reduced the lateral diffusion, and it can has this very small alpha factor. So when talking about why we have this better tolerance to coherence collapse. So coherence collapse is just a critical factor F. So this is related to alpha factor. So the smaller alpha factor is, the larger the critical value is. So that's why so actually because of we can measure that the quantum dot has like 10 times, 15 times the smaller alpha factor. So this 15 times the small alpha factor corresponds to 50 dB increase in the in the critical level. So that this critical level, the larger the critical level is, the better tolerance it is to the feedback, so that it doesn't have coherence collapse. And in terms of the better lifetime is like just as I mentioned in this TM image. So even with a lot of defects in its material, but because the quantum dot has this very small lateral diffusion, so that and also has very high density. So these defects can only affect a few dots, and the most dots doesn't diffuse to the defects, so they remain here and they can still work fine. So they are not affected, so they can still work efficiently. So that most of the dots can still work, so that it has good lifetime.
Yeah, thank you.
Okay, so and the next question is from Anthony Xu. So he has a question about KAUST. So the question is, do KAUST accept first-year undergrad students during their co-op term, or do they usually only accept students with more experience? Thanks.
So normally, I think for first-year student, you should focus on your course. It's not quite ready for research. But I think so. You can see we have this the summer camp and the winter camp. We have this summer camp and winter camp. So this is for like a third year or fourth year undergrad student. So then you can know more about research. You can know more about the postgraduate study. You can say, oh, is this the place I want to spend my next 5 years for a PhD study? Yeah, I think because it's just, so this winter camp and summer camp just last for 1 to 2 months. So this is better for experience, right? And I think after you get enough courses, you have enough background. So in your third or fourth year, you are welcome to join our lab as a visiting student researcher for like 6 months. So it's a pretty long time to gain experience for your future study, and also to help you make a decision whether or not you want to pursue a 5-year PhD in here.
Thank you. So I think we have we have online from classroom. Pranav, do you have any question from the audience in the classroom?
There's no questions from the audience here.
Okay. So maybe I asked the last question. A lot of students may interest in. I saw Yating Wan has a lots of high impact journals in a few years. So could you share some experience how to do any tricks to publish and any to develop your personal professional research? Thank you.
So actually, in the early days of my PhD, I have very sad years. So I didn't have any published paper in my first 4 years. Yeah, I started by the end of the 4th year, I started to publish my first journal. So it is really a not very pleasant experience. But I want to say that it really depends on what research direction you want to choose. So at that time, I start a very completely new project. So no one we got no experience. We have to do everything from the beginning. So if you choose this direction, in the very beginning, it's going to be very tough. But eventually, when you finally make it, you are the first one to do it. You are the pioneer in this field, and you will get the biggest of credits. Right. So, but if you choose some path that is well established, you get a lot of like previous work, like previous experience. So in the very beginning, it will be easier, right? It will be much easier. You can publish your first journal in the first 1 to 2 years, but you are not the pioneer in this field. So the previous people who experienced the hard part will get this credit. So it really depends on what direction you choose and whether or not you can finally make it, because there is also very high risk. It's possible that even in my 5th year, I still couldn't make it, and I still didn't graduate. But there is also a possibility that you take a very hard task and you start from the beginning. You experience the long, no production time for like 3 to 4 years, and finally you make it, and you got all the credit. So actually, starting from my 5th year, I published 3 to 5 journal papers every year, and then now I kind of slow down because I try to target for a higher. Like I try to limit the paper number, but increase the paper quality.
Yeah, thank you so much for Dr. Wan's today's excellent talk. So we have run out of time. So if you have further questions, so you can either send emails to Dr. Yating Wan or send to us, and we can share the answers. Oh, by the way, this seminar we have already recorded, so later we will share this videos online. You can see the notice. Okay, thanks again for Dr. Wan for this talk today. Thank you.
Thanks, see. Bye bye.
Yeah, see you. Bye bye.